Hello all, I'm Tejashree. Today, I'm going to talk about development and validation of edge-adapted, lightweight deep learning models for point-of-care oral cancer screening. This work is a part of my PhD thesis advised by Professor Rajesh Sundaresan at the Electrical and Communication Engineering Department in the Indian Institute of Science, Bengaluru. I am thankful for the Center for Networked Intelligence for generously supporting my work. To begin with, let us look at the problem. India contributes to over one-third of the global oral cancer burden. With over 140,000 new cases diagnosed annually, it is largely an Indian problem. This high incidence can be attributed to the socio-cultural use of risk factors such as tobacco, arecanut, betel quid, and alcohol usage. About 80,000 individuals succumb to the disease every year, and this high number is mainly because about 80% of the cancers are diagnosed at an advanced stage. Although these cancers could have been detected earlier, we miss them mainly due to poor access to specialists, especially in the rural and low resource settings. Prior studies have shown that oral visual examination is an RCT proven method for early detection of oral cancer. Despite that, the screening coverage is less than 2%, with the frontline health workers, or in other words, FHWs, overburdened with multiple tasks and variability exhibited by them despite training in performing oral visual examination, the access to specialist level diagnosis at the primary care centers remains a major challenge. Therefore, we propose a point of care AI enabled mobile phone based tool to solve this problem by task shifting specialist level screening through AI in the hands of frontline health workers, thus empowering them. To build such an AI model, we needed access to a large dataset. Thanks to Biocon Foundation, who generously shared their past oral cancer outreach program data with us. This data consisted of over 30,000 images captured through various smartphones from multiple parts of the country. Each image had an associated telespecialist diagnosis label, which could be further categorized into non-suspicious and suspicious categories based on the presence of oral precancer or cancerous lesions. The 30,000 image data was cleaned and categorized into training, internal validation, and internal testing set. We performed several experiments using multiple lightweight deep learning architectures. In our experiments, we found out that mobile VIT V2 gave us the best results. On the testing set, we were able to achieve 87.1% sensitivity and 86.5% specificity. Here is an illustration of how interpretable the trained models were. Here is an example of a suspicious image. The second image highlights the regions that contributed most to the model's inference. The model inferred that this image is a suspicious image, and the regions in red were the ones that contributed most to this inference. If we now compare the red region to the one in black in the third image, which is a ground truth annotated by a specialist, we can observe that the model's heat map as well as the ground truth provided by a specialist align well. The model development journey was not unmet without any challenges. One among them was that of the class imbalance. The retrospective dataset consisted of only 16.5% of suspicious images, whereas 83.5% of them constituted the non-suspicious class. Second, there was domain shift between the retrospective data on which the models were trained and the prospective data on which we wanted to validate the model's performance. As can be seen from the red, green, and blue channel histograms, there is difference in the data distribution, especially in the blue channel, causing significant domain shift. Therefore, we came up with an optimized AI development pipeline as outlined in the flow diagram, where we included specialized image preprocessing techniques such as white balancing, and included augmentations based on EXIF orientations and random rotations for better generalizability. Once the models were developed based on the optimized AI development strategy, we wanted to evaluate them on prospectively collected data. And for this exercise, we chose about 5,600 participants' data. The case level performance of AI on these participants was compared against a tele-specialist diagnosis for these cases. The green dot in the ROC curve represents the performance of the AI model, whereas the black diamonds represents the performance of FHWs in two different settings. As can be seen, the AI model exhibited a higher sensitivity as compared to the frontline healthcare workers, therefore enabling higher detection of precancers and cancers in the real-world settings. Further, we wanted to develop a risk-based three-class classification model. Here, the goal was to classify every oral cavity image into not just non-suspicious versus suspicious categories, but also do a finer classification of categorizing the suspicious lesions into low-risk and high-risk lesions. This enables higher priority for high-risk lesions in the referral recommendation. For this task, we came up with a mobile VIT-V2 based unit multitask model which not just does classification but also performs segmentation. The classification performance of the three-class multitask model is highlighted as a confusion matrix on the slide. Further, when we now compare the previous binary classification model and the current three-class classification model, we see that when the three-class classification model is reduced to binary classification, the best performance has a higher sensitivity than the best binary classification model, thus showing that training models for categorizing suspicious lesions into low risk, high risk enables models to pick up more lesions than the best binary classification model. Here is an illustration of how interpretable these models were. Here is an example of a high risk suspicious image associated with a ground truth mask provided by a specialist. In the second row, we can see the segmentation mask provided by the model, which aligns well with the ground truth mask provided by the specialist. The intersection over union is about 0.84. The model also rightly classified this image as an high-risk suspicious image. Thus, the three-class classification models enables priority referrals as well as provides enhanced interpretability. Here are a few images from the field visits where we collected the prospective data which was used for AI validation. Thank you.